The purpose of this lab was to examine and understand the motion of the swinging and oscillating spring mass system. We did this using Newton's second law, the energy principle, and Hooke's law. In the end, we found that the predicted motion of the spring mass system followed the same pattern as the observed data from Tracker, so the model was a good fit for our data. Also, we determined that this system satisfied the energy principle. The physics principles used in this lab were Hooke's law, Newton's second law, and the energy principle. After I opened the video in Tracker, I set the calibration stick equal to 0.7 meters. I put the origin at the point where the spring is attached and the spring mass system is in the negative y direction. I then took the x and y position data and copied it to a CSV file, which I then used in my code. First, I plugged in all the initial conditions into the code. Here's the given mass of the object attached to the spring, the initial position obtained from Tracker, the initial velocity, which we know to be 0 meters per second because the motion started from rest, and the initial time, which is t equals 0 seconds. Here's a CSV file containing all the position values obtained from Tracker, and then this is our time step, which is 1 over 210 seconds, and then here's the gravitational constant g, which is equal to 9.8 meters per second squared, and both of these were also given. Next, I used these equations to solve the spring constant and the spring's relaxed length. First, I found the period of oscillation, t, which is calculated to be 1.52 seconds. I then plugged this value into the equation to find the spring constant Ks. I found this to be 6.869 newtons per meter. L naught is the spring's relaxed length. This is equal to 0.1264 meters. L is the part of the code that calculates the length of the spring at each time interval. L hat is the spring's direction, and S is the stretch or compression of the spring. So this part of the code computed system energies. The kinetic energy is equal to 1/2 mass times velocity squared. The gravitational potential energy is mass times g times the object's y position, and the potential energy of the spring is equal to 1/2 spring stiffness times s squared, where s is equal to the stretch or compression of the spring. This is our calculation loop for the motion prediction of the spring mass system. We got our time from Tracker. Here we defined our initial energies. Here's the gravitational force with mg in the negative direction. The force of the spring is equal to Hooke's law. F net is equal to the sum of the spring force and the gravitational force. This value is then used in a manipulation of Newton's second law to predict the new velocity of the spring system. The position is then updated when the velocity changes at each time interval. These lines of code update the spring. Because we found the new position during each interval, we can find a new length each time and then use this to find a new L hat and new S. We can again use the lines of code previously defined to update the energy changes of our system, which we do here. This is then graphed for us in a window when we run our model. Here's the visual model for the predicted motion of the spring mass system. The red ball is representative of the data from Tracker, and the blue is of the computational model. They are closely following the same path, so my model is a good representation of my data as it is a close prediction of the data obtained from Tracker. The few discrepancies where the red ball and the blue are slightly apart are most likely due to human error when I was plotting the positions in Tracker. Here's the graph for the energy changes computed in the model. The blue line is the change in kinetic energy, the red is the change in spring potential energy, and the green line is the change in the gravitational potential energy. The yellow line is the change in the total energy of the system, which, as you can see, equals 0. The energy principle is satisfied because energy has been conserved. The change in total energy equals the change in kinetic energy plus the change in gravitational potential energy plus the change in the spring potential energy, which equals 0, as you can see by the yellow line in this graph. Using the data you obtained in Tracker, make two separate estimates of oscillation periods. First, by estimating the period of oscillation from the x position data, and second, by estimating the period of oscillation from the y position data. Compare the two estimates and discuss. The motion of the spring mass system in this lab is similar to a pendulum in the x direction and a normal spring in the y direction. To calculate the period of oscillation for a pendulum and thus this system in the x direction, you would use this formula here. To calculate the period of oscillation for this spring and this system in the y direction, you would use this formula here. As you can see, the period of oscillation for x is 1.634 seconds, and the period of oscillation for the y direction is 1.52 seconds. The two differ because the two are calculated using different equations. Thanks for watching!